Today's lesson is on simplifying radicals and adding and subtracting radicals. When we're simplifying radicals, some radicals can be simplified into integer answers like we studied in the last lesson. Like the square root of 16 is 4, because 4 times 4 is 16. The cube root of 8 is 2, because 2 times 2 times 2 is 8. And the cube root of negative 8, because 3 is odd, we're allowed to take the cube root of a negative, which gives me negative 2, because negative 2 times negative 2 times negative 2 is negative 8. Now, not all radical expressions will simplify into integers like we just did. So here are some examples that don't simplify. The square root of 17 doesn't reduce, so we're just going to leave it the square root of 17. The cube root of 16 reduces into 2 cube roots of 2. And the square root of 20 reduces into 2 square roots of 5. Now, I know you don't know how to simplify these just yet, but I want you to understand that some radicals will simplify into integers, some of them don't simplify at all, and some of them simplify into smaller, reduced radicals. Although some radicals can be simplified, some will never reduce into integers as they are written. When we are simplifying, I want you to use the following steps. Factor its radicand into its prime factors. Then I want you to look for groups of numbers equal to the index. For example, find groups of 2 for square roots and groups of 3 for cube roots, and so on and so forth. Groups will go out of the radical and be written once per group on the outside of the radical. Any factors without a group will stay under the radical. Let's practice. For the square root of 12, it says to first factor the radicand into its prime factors. So I'm going to break 12 down into 4 times 3. You could have used 2 times 6. It really doesn't matter what you start with because you're going to keep going until all you have is prime numbers. So I have 2 times 2 times 3. 2 and 3 are all prime numbers and they don't go any further. So now step 2 says look for groups equal to the number of the index. Now this is a square root, so we're looking for groups of 2. I have a group of 2 right here. I have 2 2's. So groups will go out of the radical, but I'm only going to write them once per group. And any factors without a group will stay under the radical. Now I have a little story that goes along with this. After you factor 12 into its prime factors, I kind of like to think of this square root symbol or the radical symbol. Kind of looks like a house, okay? It's like a roof of a house, okay? And inside the house we have 2, 2, and 3. Now if you have a date or someone exactly like yourself, you get to go out of the house. That's why we write the 2 on the outside, because 2 has a date. They get to go out on a date. Aw, poor 3, he doesn't have any date, so he has to stay home. So that's just one quick way that I try to remember which one's which. On square root of 98, again it's a square root, so we're looking for groups of 2, but first I need to factor out the radicand. So 98 is kind of large. If you have a hard time with that, you can always just, if it's even, divide by 2 until it gets smaller. Oh, 49, okay, 7 and 7. So sometimes you have to use your divisibility tricks or rules to help you divide large things down into smaller things that you can divide. In this case, does anyone have a date that gets to go out of the house? Well, it looks like 7 has a date, so he's going to go out of the house. Oh, poor 2, he doesn't have a date, he's going to stay home. On the next one, it's a square root of 150. So I'm going to break up 150 to 15 times 10. If it ever ends in a 0, I always use the 10 to make it much smaller. Then I have 3 times 5 times 5 times 2. Okay, who has a date here? Well, it looks like 5 gets to go out of the house. And underneath the radical, 3 does not have a date. He does not have anyone exactly like him. 2 does not have a date, so he does not get to go out. So both 3 and 2 have to stay home under the radical. Now, if you ever have more than one thing outside of the radical, or in this case, more than one thing inside the radical, they're just going to multiply, and that will be your final answer. On these next problems, I have cube roots. So this is a cube root, so I am now not looking for a pair, I'm looking for a group of 3. So I have 4 times 10, 2, 2, 2, and 5. And I'm looking for groups of 3 this time. I know that dating thing doesn't work real well with cube roots, but okay, these 3 people get to go out of the house. Notice I only write it once because they all went in the same car, okay? They're all going somewhere together. Underneath the cube root, you still have the 5. He doesn't have any groups of 3, so he has to stay inside the radical. Now, one common mistake students will make is they'll forget to keep bringing down the cube index on their answer. So please don't make that mistake because I can't give you full credit if you don't bring your cube. On the next problem we have 54. 54 is 9 times 6. And then we have 3 times 3 times 3 times 2. And because we have a cube root, we are looking for groups of 3. I have one group of 3 here. Don't forget your cube root on the house. And then 2 stays inside. 240 looks like we have 24 times 10. And then 6 times 4. 2 and 5, let's see, 2 times 3. Now, I like, after I've done this, if there's any prime factors that are not on the same level, I like to bring them all down so that I don't forget some factor that's kind of hanging out somewhere else high. Alright, I'm looking for groups of 3. Looks like I have a group of 3 right here. So that 2 gets to go out of the house. Inside my cube root, I have a 2 left, I have a 3 left, and I have a 5 left. So I multiply anything that's left inside the house or anything that's left outside the house, and that looks like I'm getting 2 cube roots of 30 as my final answer. Alright, now we got a 4th root, so now I'm looking for groups of 4. So 48 is 4 times 12. 2 times 2, 4 times 3. Don't forget to bring all of the numbers down so they're all on the same level. I'm looking for a group of 4 this time. I've got one group of 4 of 2s. So that group gets to go out. I only write it once. Inside the 4th root, don't forget the little index of 4, the lonely 3, he has to stay home. And now that is completely reduced. Now, we just reduced 240, didn't we? We can probably use the same one. Just going to rewrite this over here. The same exact prime factorization, but this time I'm looking for groups of 4. So I have 4 2s right here. So that group of 2 gets to go out. Inside the 4th root, I have a 3 left and a 5 left. So my final answer is 2 times the 4th root of 15. On our next problem, it looks a little bit different, doesn't it? We have x's and y's. Okay, well, if you think of x cubed as x times x times x, and y squared as y times y, well, you could just write them out in its prime factorization, and because this is a square root, we're looking for groups of 2. So I have a group of 2 of x's, and I have a group of 2 of y's. So the x goes out, the y goes out, and the lonely x has to stay inside the radical. Now that is a fine way of doing this problem, but what if the exponents of 3 and 2 were much, much larger? You really wouldn't want to write out like 47 x's and 52 y's, right? That would take a little bit of time. So one shortcut you could do is look at the 3 and divide it by the index. So 3 divided by 2, that's one whole. So that's one whole group that gets to go out of the house. And then how many leftovers do you have after you've taken away a group of 2? Well, you only have 1. So you could probably think about that in your head. So 3 divided by 2 is 1, leftover 1. The 1 goes here, the leftover 1 goes here. And then on the second part, I could take 2 divided by 2, and that gets me 1, so that's one group of y. And notice I don't have any leftovers, so that's why there's no other y inside the radical. That's another way you could possibly do this. So doing more of these problems, I could write the 3x's out and the 2y's out and circle my groups of, in this case, 3. So the 3x's come out of the house. Notice I only write them once because I only write it outside the house once for each group. It's like they're getting in the same car. Now y times y. I have 2 of those, but I would need 3 of them for them to leave the house. So these 2 will just stay home. Again, a shortcut way of doing that would just be, instead of writing out all your x's and y's, you could just take 3 and divide it by 3. Well, that gets me 1. And the 1 whole gets to go on the outside. Is there any leftovers of the x's? Well, no, there's not. 2 divided by 3 is 0, so I can't have anybody come out, and then the 2 leftovers stay home. On our next problem, we have a 4th root, which means we're looking for groups of 4. If I were to write this out, and now this is now getting just a little bit long, I don't want to really write this many, but technically you could. So I'm looking for groups of 4. I have a group of 4 of x. I come out, write it once, no leftovers on the inside. I have a group of y of 4 y's. So that one comes out. There's only 1. That's the exponent of 1. But there is one leftover y here. And on z's, I have one group of 4 of z's. So one group comes out. And then the 2 leftover z's are left inside the radical. This is my final answer. Going through the shortcut one more time. 4 divided by 4 is 1. 5 divided by 4 is 1 left over 1. 6 divided by 4 is 1 left over the 2 right there. Okay? So that might help you, especially on this next problem, when you have a very large radicand. So the 4th root of x to 100, y to the 52, and z to the 31. I will not write out 100 x's and circle them in groups of 4. That's just ridiculous. But I could do my shortcut. If I have 100 x's and I'm looking for groups of 4, you just take 100 divided by 4, and that gives you 25 groups of 4, and they all come out. There isn't any leftovers, so nothing else gets put inside the house. Y to the 52, so on that part I'm going to take 52 and divide it by 4, and 52 divided by 4 gets me 13 with no leftovers at all. So I have y to the 13, that's the number of groups of 4 that I can come out. I don't put any y's inside the radical because there's no leftovers. Okay. For z, I'm going to take 31 and divide it by 4. And 31 divided by 4 is 7. So that's z to the 7 with some leftovers though, because 7 times 4 is 28, which leaves me with 3 leftover z's. Any leftover z's are going to go inside the radical. Just to make sure you know you're done, all of the exponents inside the radicals should always be smaller than the index. If they're not smaller than the index, that means you're not 100% reduced. But since 3 is smaller than 4, we are reduced.